Okay, Tim is going to talk about JRuby on elephants. Round of applause.
Okay, should I take that? I want to talk a little bit about using JRuby with a couple of interesting Java libraries, one of which is Hadoop. It's a MapReduce framework, which is a complicated thing that Google came up with for doing big stuff with data very quickly on parallel machines. I won't go into that too much. So the type of things this is used for is big data-intensive computations, things like analytics, things like search, things like machine learning. There's also this fantastically useful set of libraries called Mahout, which kind of provides a sort of abstraction layer over the top of Hadoop, specifically for doing machine learning. And in fact, the way it's turned out is the stuff I'm going to show you today doesn't actually use Hadoop at all. It uses some stuff that's just internal to Mahout, but there are options there if you want to do stuff on, billions and billions of rows of data. So, where did I go? What I'm going to talk about, a minimal bit of the kind of theory of these things and why you might want to do them and the sort of things you might want to do. Then a sort of case study, which is called kitten detection with Mahout and JRuby, which I will get onto later on. I'm going to talk a little bit about some sort of interesting quirks. I mean, maybe they're not that interesting, but I got stuck on them while doing this, involved in calling Java code from JRuby. Various ways of sort of overcoming the unpleasantness of working with Java. And then a little bit on how to sort of evaluate how well these type of techniques work and sort of just basically see if they're any good or not. So to start with, machine learning. There are two types of machine learning problem, broadly speaking. You have supervised learning and unsupervised learning. Now, supervised learning is a bunch of techniques that broadly involve learning by example. You have an algorithm and you sort of show it a few examples of the right answer to a question, and then once it's learnt from them, it can sort of start to infer patterns in other new stuff. Supervised learning includes classification, which we're going to talk about now, which is taking things and sort of putting them in buckets depending on various properties of them. Ranking, which involves taking a sort of set of things and putting them in an order, and regression, which is predicting a sort of real valued number from a set of properties. Unsupervised learning is slightly different. It's to do with finding hidden patterns in data. So you might not know that there's a sort of particular pattern there, but it can pull out clusters or sort of patterns within stuff. And the important thing with this is to sort of interpret those results well, because you're not, there's no real kind of semantics to it. If you chuck a whole bunch of data points and it comes up with clusters, they may or may not mean anything because you haven't really defined what it means. But it's quite useful for kind of looking for patterns that you didn't know were there. Unsupervised learning, as I just said, involves clustering and collaborative filtering, which is doing recommendations where you have profiles for users and things that they like in some sense, and sort of recommending things to people. So Mahout can do all this stuff, and it can do it on huge data sets using Hadoop to do kind of massively parallel stuff, which is awesome and very useful. The only trouble is, it's written in Java. So we have to, I feel a bit bad actually after Tom's talk about the wonders of object-oriented design to come up with that. And also, to be fair, that's not the Mahout JDoc. It's nowhere near that bad, but it's still a lot of fun. So thankfully, we have JRuby. So what we're going to do is use JRuby to go through an example of doing classification. And what we're going to do is try and detect kittens in people's Twitter messages. So looking at a couple of tweets there, I'm using, rather than going through Twitter myself and finding tweets with pictures of kittens, I've used links to cuteoverload.com as a sort of useful proxy for cute fluffy animals in Twitter messages. There we are. So what we're trying to do is trying to find the patterns in messages like this, messages that include a cute overload URL that separate them from ones like this, or like anything else. And I do realize the URL's a dead giveaway, but we'll come to that later on. So our first approach to this might look something like that. And yeah, that pretty much works. Okay. There's one thing we've missed out there, though. That only works in the situation where we know what are good indicators for the presence of kittens. We don't. It's because we can people are so utterly predictable. You can tell exactly what words are going to be used, and you can build a regex. But in some cases, the space of features you're going to be looking at is far too complicated for you to sort of be able to look at that yourself. So in this case, we'll sort of pretend that's the case here and carry on. So machine learning, the whole point of it is allowing our system to find those features, to isolate those things itself, rather than us having to tell it exactly what features of the kind of set of data are pertinent to our problem. So this is a classification problem. As we mentioned before, we're taking a whole bunch of Twitter messages, and we want to put them into the kittens or no kittens bucket based on a bunch of features, and we're going to do that by seeding it with some that are already labeled and allowing it to learn. So this uses techniques from statistics called logistic regression, which I'll go through very, very quickly because it's not very interesting, but just to give you an idea of what we're doing. So, oh, that's a shame. That doesn't really show up. What do I do with the thing? So up the top here, we've got some red squares, and down the bottom we've got some green, or they're all crosses, sorry, red crosses and green crosses. And you can see that roughly red ones tend to be high up on the y-axis, and green ones tend to be quite far down. So we want to find a way of predicting whether something's red or green from its sort of height on that axis there. Oh, really? Right. I think I might have to have a short break. Sorry about that, and I hope, all you Mac users can be justifiably vindicated, I guess. So before all that went wrong, we had these points here. We have the two different sort of heights. You have a value going from 0 to whatever up there, and you've got some which are green and some which are red, depending on the height. So you want to predict what colour something is going to be based on this value here. So one way of doing it, logistic regression draws a sort of S-shaped logistic curve and it finds the sort of values, the parameters of that curve from the example points you plot it. And the value of that graph is the probability, in this case, the value at any given height is the probability that a point at that height will be red, given the value and given theta, which is the parameters of the model we're using, which I'll come to later. So there's a kind of sound bit of mathematics for doing these kind of things, which you don't really need to know because Mahout handles this for you. So the first kind of challenge then is to turn the text of these tweets into numbers so that we can perform all this kind of mathematics on them. So you turn each training or test example into a vector where you have a big kind of essentially array of numbers where each position in the array represents one word in the sort of the entire corpus of words you're dealing with. So a sort of easy way to do that is just count the number of times each word appears in each example. But that's kind of a little bit naive and is perhaps slightly flawed because some words are more useful than others. If you have a message that has autohagiographer, then that's presumably going to be more significant than because or the or and. So there's a couple of ways of dealing with this. The first is stop words, where you keep a list of all the kind of words in a given language that are semantically kind of meaningless, like articles and the a and just stuff that is kind of just becomes noise, essentially. So you can filter out stop words, and then you can do something a bit more clever where you weight each term frequency by it's the log of the number of documents that word appears in. So if a word appears in loads and loads of documents, you assume it's less significant than if it appears in just one or two. The other problem you have is that some words are really kind of talk about the same thing. So you want to make sure if you have kind of plurals or different forms of verbs that you're actually counting them as the same thing rather than counting them a million times in every different form. So the first thing you have to do is obviously split the whole string into words, correct for kind of case and punctuation and stuff, which is what normalization is. And then you can do a process called stemming, which is an algorithm that goes through words and reduces, applies these rules and reduces them down to their stemmed forms. So what ends in SSIS. So dresses would get reduced to dress, whereas something ending with a single S, like kittens, would get reduced to kitten. So these rules keep words that do end in S and get rid of plurals and reduce each word down to its kind of stem. Paul told me what the word for this was. The root, was that right? Yes, yeah, the root form of that particular term. So once you've done that, you've hopefully pulled out a lot of the kind of noise from just sort of all the very common words in English, and also I sort of normalized everything so that each kind of word has only one representation in this vector. So this is the kind of process it would go through. You take your input text, get split out into tokens, normalized by case, and then the stop words, so the is taken out, and then the stemming removes the sort of adjective form, no, this is superlative, isn't it, on the end of there, and so you end up with just two words which kind of uniquely describe those two concepts. So what we use for this is another fantastic Java library called Apache Lucene, which is used for making search engines, basically, and it has loads of text manipulation stuff for doing all this kind of stuff, and it's fantastically easy to integrate with Mahout, which is nice, because they're both Apache projects. So here's my kind of little Ruby wrapper around Lucene stuff, and I'll look into the sort of internals of this in a bit. But you can, there's my pointer thing, you create a text analyzer, and then you, in order, you tell it what filters to use. Standard filter just splits words out. Lowercase filter lowercases them all. You then have a stop word filter, which has to take extra parameters, hence this slightly ugly block here. And then a porter stemmer, and you just apply these in the order you want them to be applied, and it will go through the text, applying each of these things, and eventually ending up with a stream of tokens you can use to create your vectors. So from that, you can then create a model. You need to do this, you need to get some training data, which we have. We have a huge list of big CSV file with Twitter messages, which are marked as either having a linked Qt overload or a link to not, or no linked Qt overload. We've got about 3,000, which isn't really enough. It's not hugely many, and the other point is Mahout isn't very good on small data sets. It's not very quick. It kind of comes into its own when you're dealing with millions of billions of rows because of the kind of inherent cost of parallelizing stuff over lots of machines. But if you're dealing with just a couple, then you may as well use R or something else, because it'll be a lot quicker and easier. But this is an example to show off how it works, so we'll ignore that. So what we're doing, again, is a supervised learning technique. We're taking examples, and we're giving them to the machine learning thing to learn where that logistic curve should sit that will separate kittens from not kittens. So we have a slight problem, though. If you go back to, and should have put that slide in again. Where's DHH? There he is. If you go back here, then there's a massive kind of giveaway in that the text contains the URL which we're using, which is what we're trying to learn. And this is what you call a target leak, because there's a single, there's a sort of single feature in there that helps the model cheat. It can identify that one thing, and it will always get the right answers because that's the thing it's looking for. And then what happens then is when I find a whole bunch of other Twitter messages and I want to look for kittens and it's not a linked Qt overload, it'll do really badly because it's looking for that one thing and not learning from anything else. So what we need to do first is strip out the URLs. So here we've got a little preprocessor block which strips out kind of pertinent stuff that we want to avoid in order that our learning thing doesn't sort of overfit to sort of giveaways of what the answer is. So from that, we can then train the model. So you create our new logistic regression classifier, which has two classes. It's either yes or no, and you pass in that analyzer we just made. And then for each one, you just go through your training data, which in this case is a big sort of two-dimensional array, get the text in the category, and train the classifier. And then after that's done, we can use it, we can test it out. So I'm going to show you quickly sort of how the internals of some of that stuff works. Just to give you an idea of kind of how ugly the Java code is and how Ruby can make it nicer. So what you just saw is this. We create the analyzer.
Can you make that bigger?
Oh, maybe. Oh, fantastic.
Any bigger?
A bit bigger.
Say when.
Smaller.
Is that all right?
Yeah.
Thank you very much. So we have, as you saw before, we create this analyzer and classifier and use them together. And really, once you've created the classifier, all you're interested in is this train method, and then this, we have a test method and the classify method, and I'll show you what they do. But inside these, sorry, 1 second, this is, so inside the analyzer first, all we're doing is extending Lucine's internal analyzer, then using a little bit of kind of Ruby stuff to make it a little bit nicer, a bit more configurable, and we keep a list of filters we want to apply, and then when it comes to create the token stream, we just inject over that list, passing in the tokens and just calling them all on each other, and then it sort of puts them together. So there's no need, if you want to plug a new filter in Ruby, and if you do this in Java, you then have to define a new analyzer which specifically takes that particular filter class and does something with it, whereas because we have dynamic dispatch and we can pass class references in, which I think you can do in Java somehow, but it's a massive pain, we can then just construct this list of all the classes we want to use, and then at runtime go through them, instantiate new instances of them, and chain them together. Where's the classifier? Sorry. So inside the classifier itself, you have a whole bunch of just kind of controls you set really for doing various things, which are defaults, and these can be passed in as parameters. And then this handles all the creating the vector, passing it into the classifier and getting the results out, which in kind of plain old Mahou is a bit of a pain. You have to, so for instance, to get an example out, you create a new vector of the same size as the number of classes and then look for the number in that which is the maximum, which isn't massively intuitive. So we instead we can kind of encapsulate this within this classify method, and then it will just return the number of the class that it is. So we don't have to worry about all the kind of plumbing internally. We've also got a method called test, which will take an example and the category it's in, and we'll check to see if it got it right. So it will return true or false, depending on whether or not the classifier accurately predicted what it was meant to be looking at. So there's a couple of, I spelled that wrong, sorry. There's a couple of interesting things I found out about JRuby while doing this. I'm going to go over very, very quickly. The first is if you compile JRuby into a class file, if you use any of the Ruby standard library, you need to include this JRuby complete jar, which helpfully doesn't come in the standard JRuby distribution. You have to go and get it from elsewhere. And then if you put that on your class path, you can use things like the CSV library and test unit and anything that's in the Ruby standard library. But if you don't do that, you can't. And it's not massively obvious, or it wasn't to me, but that's worth bearing in mind. The other thing is when you have a class that's been imported from Java, you have the .class method refers to a sort of Ruby object that wraps the Java class. So if you need a reference to the Java class for some kind of dependency injection Java thing, then there's this other Java class method which gives you that, and that I wasted hours working that out. The other thing that happens is using generics, type information is erased at runtime. They get, after it's been compiled into sort of JVM bytecode, the type information's gone. So if you've got anything that relies on having a generic collection of a specific class, it won't see it, because everything just becomes object once you've gone past the compiler. And this also has a bearing on overloaded functions. So for instance, you have two functions of the same name, one that takes a string and an int, and one that takes an object and an int. You can't guarantee that it'll call the string one, even if you pass a string in, because it doesn't know, because of type erasure, that that string is a string. So in order to do that, you can kind of hint it by using JavaSend, and you pass in this array of types for the function you're looking for, and then that will guarantee it will find the right one. So finally, I'd like to talk a little bit about evaluating this kind of work. The important thing is to test on a set of data that is different to the data you trained on. So at this point, we're taking our entire list of tweets, shuffling them, and then dividing it in two. So we've got a separate set of examples to train and to test on. And this this is important due to the overfitting problem we talked about earlier on. If you test off the same data you trained on, it's very easy for it to get stuck in a sort of loop where it's looking at very specific things and then can't generalize out to other examples later on. The other thing you need to do is then sort of somehow quantify that. So we have a bunch of metrics we can use. The simplest is just the proportion guessed correctly out of a certain set. You go through a whole bunch of things, count the number of guesses it got right, and count the number of guesses it got wrong. There's another slightly more complicated metric called log likelihood, which is useful but slightly more difficult to explain, and that's the probability that the classifier will be correct given a certain example, which isn't worth bothering about. And then for different types of problems, stuff like ranking and search problems, you can have a whole slew of different types of numbers that you can use to quantify this stuff. But in general, all you're interested in is how many examples did I get right. So, in fact, rather than showing you the numbers, I'll actually run this thing and show you. Let's have a look. We have Ruby scripts. Okay, so we've run this Ruby script which I showed you earlier, and in 10, 20 seconds normally, it'll, spit out a list of examples. So we can see immediately they got 93% of the testing examples correct, so we can accurately identify kittens using statistics, which is a useful bit of technology to have, I think. And we've got a few examples of where it guessed correctly. So if we look, here's a target leak, which we didn't take into account, that the name of the site might appear outside of the URL. So that would be another thing to look at in the future. However, it's... that's a shame. They both got the text in, and honestly, it wasn't doing that earlier. I think that's just this particular run. It does work in a slightly more general way. But then you can also look at the ones it got wrong. So down here, for instance, we have or how about this, which really, there's no kind of pertinent words at all in there, so it's not massively surprising that it didn't guess that. And in fact, this is, this is sort of, in fact, that's kind of surprising. Google and React is, not very, I don't know, but in general, it seems like it's guessing wrong on things that are quite difficult, apart from this sort of screamingly obvious one here, and various other things. But if we run it again, hopefully we'll get a better set of examples. I'll try. I'll admit defeat if we don't. It doesn't work this time. Okay. So where have we got? Oh, that's interesting. So this one here, it's worked out from very little that is. That is an example of a cat picture. I can't get that URL out, but that's clearly what's on it because it's on that website. And you can tell that it's managed to sort of separate the two classes out, looking at just the text of the Twitter messages. Thank you. There you go.
Thanks very much. Is this on?
Have I broken that as well?
Oh, the Linux curse. So you don't have any questions for Tim? Oh.
You can shout as well.
No.
Is there any way of saving off the classifier after you've done the training?
Yes, there is. I didn't do that for this, but it creates a sort of huge model file, which is, I don't actually know how you interpret it looking at a disk, but it has the kind of facility to save it out, which is obviously very important if you're training this thing and using it over a huge period of time. There's quite a lot of information stored in there, and especially when you know, it could take hours or days to actually produce that model if you're dealing with loads and loads of data. It's quite important. But yeah, Mahout will let you save stuff off to a file. And in fact, there's a command line interface to it as well that I didn't touch on because there's loads of tutorials and stuff for that around on the internet, and actually using it from within code, less so. But there's a command line thing you can call and pass it the location of a certain model file, and it will sort of deal with all these things from there. So yeah, absolutely.
I don't know if you mentioned, but what was the primary motivation for you to use JRuby? Is it just because the Mahout is written in Java, and if it is, then that's the necessity?
That was, yeah, well, that was pretty much it. I was looking for a way of sort of using Mahout from kind of our own applications without having to write Java, because I really don't enjoy it. So that was the kind of main motivation for it. In fact, there is this kind of, you can get to it very happily through the command line, so there's no real need to use a JVM language. You can just kind of call out to the shell and call the Mahout with command with various arguments, which will do just fine as well, but it sort of seemed like an interesting challenge to do it this way, really. Yeah, that was pretty much it. I would possibly have used Scala as well if it hadn't have been a Ruby conference I was presenting it at. So, but yeah, that was the fact that it was on the JVM was the main kind of driver for that.
And are you using this professionally? Can you just tell us anything about what you're using it for and how it works?
Henry can wave and shut me up if I tell you too much detail. But we use. So I work at a company called Likely, and we have lots of Facebook pages and Twitter feeds and stuff which are geared towards very small local areas. So we have sort of little neighbourhoods of London and things like this. And we have a sort of editorial team who go through and find useful and interesting things for these little communities. But then it's quite difficult to find stuff sort of ahead of time, find things that, you know, haven't already been shown on God knows how many different blogs. So we've been using this to kind of try and learn a little bit about what our audience likes, and so by looking at the text of things that have got a good response before, looking at trying to infer whether something is relevant to a certain location or not, and then in order to make suggestions to our editors so that they can find stuff that that people will be interested in reading. So that's a little bit vague, but yes.
Hello, Tim.
Hello.
Up here.
Oh, hello.
I wonder if you could tell us a little bit about failures for the classifier to identify correct ones versus false positives, and whether it requires it to be conservative or over-eager, that kind of thing.
Okay, that's a very good point. I guess, yeah, they're both risks. I don't not entirely sure how you'd sort of mitigate against or sort of bias towards one versus the other. I mean, in that case, we got quite a lot of false positives because it had clearly learnt two words kind of higher than others, but it's quite difficult to kind of, I mean, if anyone knows a way, please tell me, to sort of identify that programmatically and sort of bias what you're doing towards a kind of towards either coming out positive or negative. So you can do this by sort of evaluating the results of things yourself and then sort of trying to identify what that means and how to improve things. But I'm not entirely sure how you'd go about sort of building that in automatically. So sorry.
Sorry, I think we're out of time.
Sorry. Yeah. Thank you.